second to last chapter 6 video. We are on section 6.3 and I'm doing question 135. But first, a quick overview of section 6.3 and the most important concepts that we've applied and I would probably need to learn for going into the next type of calc. In this chapter, we are dealing with finding Taylor polynomial of a given order for a given function. So what that pretty much means is that there are power series out there, but among those power series specifically, there is such a series called a Taylor series where if there is a function f, then as you take the derivative of it, like if you keep taking the derivative of it and it has derivatives on like the order x equals a, which is I guess how do I explain it? It's just from the original form of the power series, where it's supposed to be c sub n times x minus a to the power of n. If x equals a of this function, then the Taylor series can be written and expanded using the following formula, which is the summation from n equals 0 to infinity, and then it's the actual series is f to the power of n times a divided by n prime times x minus a to the power of n. So in that, what that pretty much means is if you can put it into a closed form where, if you can put a series into a closed form where it has an f to the n power times a divided by n to the factorial times x minus a to the power of n, you can pretty much find what the function is, like the what the function is, like if you keep going through the series, like taking derivatives of it, like you can find what the function is at any point, like at n equals 50, at n equals 14, like it really doesn't matter. That is what a Taylor series helps find for the function. And at 0 of the function, for f at 0, it is known as the Maclaurin series because it gives us that initial series start of the Maclaurin series, of the Taylor series. So we'll go through like how to find the Maclaurin series from the Taylor polynomial, but first I just thought that memorizing the formula, it actually is very helpful. If you were to expand it, you can plug and chug into that exact formula and keep it going, and all you would need to do is make sure that it lines up with how these equations are set up. So what that pretty much means is, say we're just using sine x as like our function. If you go through using the Taylor series approximation, you will get to the point where you can see that it goes like sine, cosine, negative cosine, and then sine again. It repeats after every 4, and the value also repeats after every 4, like the actual f at 0, f at 0 value. So it would like go 0, 1, 0, negative 1, 0. So since you see the pattern repeating, we can put that into our Taylor series where it shows that the first element in the series is just the function at 0, which would in this case be 0. Then it would be cosine at 0, which would be just I guess x, because you would need to again follow up with that Taylor series, and when you do that, like you'll get x, since you don't have like a it's just x minus 0. So you get 0 plus x, and then if you go to the second, like p2, if you plug in 0 for the second derivative of the original function, which is negative sine x, you get plus 0 again, so it still just equals x. By the time you get to the third one, you realize that now it's negative cosine x, and once you plug in 0, you get negative 1. But at this point, you have to start using the actual Taylor series approximation. So it would be 0 plus x plus 0 minus 1 over 3 factorial, since it is p3, and then that would be times x cubed, since there is no a. It would just be the function, the third derivative of the function adds 0 over n factorial. So we're at 3, so it'd be 3 factorial times x minus a to the power of n. So we're on 3, so x to the power of 3. So right now we're at x minus x cubed over x factorial. And if we keep going, we see that this keeps up with the odd numbers, with exception to the first element where it's just x. Every other odd number after that, you would just alternate the sign, and then you would raise that x to the power of whatever number you are in the sequence, and then divide it by the factorial of the number you are in the sequence. And that's a pretty closed form. You can get through that with all the derivatives, or with any series. Like, you can find a closed form that works for you. That's just a Taylor series for sine. But along with that, you can pretty much do what we've been doing, in the sense of put components together as you need it to find the optimal piece of information that you need. Like, from a series, you can find, say you have like the fourth derivative of a function, you can find the original function, and like we did in section 5, like, you can find the initial cost, like the initial value of the function given a random derivative function and what it equals at that time. You can also do approximations, like Taylor theorem with reminder is the next section that I actually did want to get into. And all that is the equation is, there's a remainder x, r sub n of x equals the original function f of x minus p sub n of x. So what p sub n is if you remember, p like p sub n of x is just the sequence of Taylor polynomials. So we don't yet know if it converges or not, but we can get the remainder using this formula. And we can also use the mean value theorem in a similar way to differentiate it. But essentially, the remainder formula is r sub n of x equals f of x minus p sub n of x. And all that means is this is a function that can be differentiated n plus 1 times on the interval, and p of n represents the nth Taylor polynomial of f of a. So the next formula that we go into is, we're just expanding the Taylor theorem with remainder formula into the full Taylor series equation that we worked with, that I just went over. R sub n of x equals f to the power of n plus 1 times c all over n plus 1 factorial, like n plus 1 in parentheses factorial, times x minus a to the power of n plus 1. So this pretty much just allows us to get into that form where we're trying to find a member of this set. So if we, I guess the final part of the Taylor theorem with the remainder is if we take the absolute value of Rn sub x, then that should be less than or equal to m, which is a number that is greater than, I guess, the numerator of this Taylor series all over n plus 1 factorial times this absolute value of x minus a, close absolute value n plus 1. So what that pretty much means is you can use the approximate, like you can use the Taylor remainder to find approximate values, to find where it is at a certain point in the series, like the nth element. You can prove the convergence of a function. You can estimate the accuracy of polynomials by approximating the function values. There's a lot you can do using that, but ultimately what we're trying to do here is we're trying to represent series as representing, we're trying to represent functions as Taylor series and ultimately Maclaurin series, depending on what the question asks. And we can also find like the convergence of that series as well, because if it does have like if it does have derivatives over that summation domain, like from n equals 0 to infinity, like if it has derivatives of all of those orders, then it does converge to f of x, which is like where we finally built into. And it only converges into f of x if that limit that we take of the remainder, like we set the original Taylor series equal to the remainder equation, like you remember, and if we take the limit of that, if it equals 0, then it converges. Other than that, it's just manipulation of the equations we just went over to find the component we need that the question is asking. I'll do one example right now. It's question 135, section 6.3 once more. And this equation is find the smallest value of n such that the remainder estimate, where m is the maximum value of f to the power of n plus 1 times z on the interval between a and the indicated point, yields a remainder approximate of less than or equal to 1 over 1,000. So question 135, it's the function that's given is f of x equals e to the power of negative x over negative 3 to 3, where a equals 0. So it's nice that a equals 0 because we don't have to plug that into the formula, and we can just say f of x equals e to the power of negative x. So the maximum we want this r of n value is once you take the absolute of the r sub n value, you don't want it to exceed 1 over 1,000 like it states in the question. So if we want that to happen, we need to figure out how the series progresses. And since it is e to the power of negative x, that will always remain constant. E to the power of negative x, the derivative will just be like, well, the function would be f of n plus 1, like depending on if it's like what term it is in the sequence, it would just be plus or minus, again, what term it is. So 1 to the power of n plus 1 times e to the negative x. Yes, so the form that I found right here is where we're going to start with, if you can see it. We were right there, we're trying to get to that approximation where it's less than or equal to 1 over 1,000, and since the function is e to the power of negative x, as each, like, if it does go through the interval -3 to 3, as it alternates, like goes from -3 to -2 or -2 to -1, then I found the f function that shows how that changes. So here we set the maximum because it is asking for the where m is the maximum value of f to the where m is the maximum value, and it gives us the equation that we should be using, which is the absolute value of r sub n is less than or equal to e to the power of 3. Because again, if you remember, we have the range -3 to 3, and if you plug in -3, then you get e to the third, which is the highest value that you could get for this, since the negatives cancel out. So you get e to the -3 over n plus 1 factorial times the absolute value of x raised to the power of n plus 1. And it's usually x minus a, but we don't have an a, so I'm just going to keep it simple and say it's x. And then we want all of that, the equation we just wrote, to be less than 1 over 1,000. So we reset that so that 1 over 1,000 is greater than or equal to e cubed over n plus 1 factorial times this x would be 3, and then raise that to the n plus 1 power, and then now we just try out like approximations for n to see when it'll just approach right under 1 over 1,000. So over 1. I'm going to use the calculator on my laptop just to do this math. E to e cubed times e cubed times 3 to the power 2 divided by 2 factorial 1 through 8. So I'm just trying random numbers right now. So far I've tried R at 1, R at 3, and R at 12. These are my results so far. I'm approaching the 0.001 value. I'm like halfway there with R at 12. So I'm going to try R at 14 and then see how that works out. So I tried R at 14 and it gave me 0.0011, which is slightly larger than 1 over 1,000. So R15 is the answer, where n equals well, technically it would be R at 14 actually, sorry. So this is my set of trial and error for the approximations. And as you can see, R at 14 gives me the approximate value right a little bit worse than 1 over 1,000. So at n equals 14, that's the smallest value such that the remainder estimate on the interval yields a remainder estimate of less than 1/1000th. And I believe that is the end of chapter section 6.3. Again, if you memorize the form, like the equation of what a Taylor series is, and understand and maintain the idea that the Maclaurin series is just the function of the first element of that Taylor series, and then if you remember how the remainder formula is, those three things are the most crucial for section 6.3 and even for section 6.4, because they can be manipulated in a lot of ways depending on how the question is being asked. I believe that is it, and thank you for watching. I will be recording my last web vlog and uploading it very soon. Thank you.